Check. People online can use type a yes if you can hear me. All right, let's get started. So not too many lectures left. I will post an announcement today on the Canvas, basically to address a few things about the final exam. Final exam will not be accumulative, okay, basically. It will pick up from where the midterm has left over. Okay. Okay, so let's continue it here. And the other thing is, can we have a little bit quieter here? So for some of you, not you guys here, for some students who's not coming to the lecture, who's not also watching the videos, probably not really helps. But anyway, so you need to further thoroughly review all these lectures, all the lecture videos, including maybe tutorial videos. Okay, if there's anything that you need to catch up, we will also think about maybe some office hours right after our lecture's over. Okay. So just a quick review of what we did. Yes, we learned about impulse response of a LTI system. So just a quick catch, and then let's finish the example. This is the recall on the definition of impulse response. If your input to the linear time invariant system is impulse function or impulse signal delta t, then the corresponding outputs of the system is called impulse response. So whatever the input, the output, whatever the output is, if your input is delta t, then it's called impulse response. And we have already confirmed that experimentally you cannot obtain impulse response because you cannot generate an ideal impulse signal. So now we learned Laplace transform. So we have an analytical way to actually derive the impulse response. So that it's proved here. It's a very simple proof. Okay? If you recall, this is a transfer function, h of s. X of s is the Laplace of the inputs, y of s Laplace of the output. If the input is impulse signal, then its Laplace is actually just 1. Then the output is equivalent to the transfer function h of s. So that's why the impulse response is simply the inverse of the transfer function of the system. So the fundamental concept that here, right, that you need to memorize, or you need to basically firmly memorize, is impulse response of the system is the inverse of the Laplace of the transfer function of the system. Okay. So that's basically the important message that we get from the previous lecture. And the example that we started is a mass spring damper system. So very simple mass spring damper system with MKB and an external force applied to the system. So there are 3 questions to this question. So what is the transfer function, and then what's the impulse response, okay. And then if the input is unit step input, then what's the system response? So let's take a look at each one of these again. First, transfer function. Transfer function is strictly derived from the model of the system. And the model of the system for this simple system, m dx squared over dt plus b dx over dt plus kx equal to f of t. A simple model of this generates a second order system. Then you take Laplace of both sides. to derive the transfer function, you don't need to know what the input signal is. Okay, so because transfer function is a ratio between a general input, a general input over the output. Okay. So once you get this, also you have to assume all the initial conditions to be 0. So then your transfer function is simply the ratio between the output over the input. So just group similar terms and write it in the fraction. So this is your transfer function. Plugging the numbers. In this question, m is 1, b is 4, 5, k is 5. Okay, so we end up with the transfer function. So from this step to this step, I did not write it, but we have assumed initial conditions is all equal to 0. Okay, so first part is done. Right, should be pretty simple. Second part is to get impulse response, h of t. So as we just reviewed, if you're looking for the impulse response, it's simply just the inverse of plus of this transfer function. So we're looking at the inverse of this function. All right. Now for this function, if you're looking at the inverse of certain s function, then you have to resort back to the lectures we did, right? What kind of case does it fall under? Basically, you look at the root or the poles of the system of the s function. Does it give you real poles or does it give you complex conjugate poles? Right? If it does give you complex conjugate poles, then we have a different part of the table to use. So this is the table we're going to use to find the inverse of this Laplace transform. Now, if you set the numerator equal to 0, then you'll find the poles of the system actually complex conjugate roots. Okay, so you cannot decompose it any further. So all you need to do is you have to rewrite it, trying to match to either this or this. Okay, so at least first match the denominator to be in this format here. So s plus a squared plus omega squared. So let's match that. Here's s squared plus 4s. So you already focus on the first two terms first. If you're more experienced, right, and you know that because this is 4s, if you want to write it into a format like s plus a squared, then you need a 4 at here, so then you can write it into s plus 2 squared. But it's 5, so then you need another 1, right, just to make it exactly the same. So then the bottom becomes s plus 2 squared plus 1. And so now you can look at the table here. So what's the table? The table, I have s plus a squared plus omega squared. So in this case, my omega must be 1, right? If I use the table to look at the numerator, the closest one is this. The numerator here is also omega, which should also be 1. So if I go back to my case study here, so I don't need to do anything at all. This is exactly a match to what's in the table already, right? So a equal to 2, omega equal to 1. Then the inverse is simply just e to the power negative 2t and cosine omega t, which is cosine t. Sorry, not cosine. Not cosine, sine. And technically, you should multiply by u of t. So to indicate, right, we're dealing with a causal signal. So that's the procedure. Right? You get to transfer function, then you take the inverse of the transfer function to get to this impulse response. And of course, for this step here, you might need to do some manipulations so that you can actually use this table, right, from the Laplace table there. Okay, so third question is when f of t is a unit step input, the unit step input is basically equal to 1, then what is the output x of t? And we have initial condition given. So here the initial condition, x of 0 equal to 0, x a derivative of 0 equal to 2. So you look at the first question, the first part of the question, second part of the question, right? You do not need to know, or you do not have to plug in any specific signal for f of t. But for the third part, then you do need to have a specific signal. So you can see if this is a real original model of second order differential equation. So now you plug in this f of t with u of t, right? So basically you have f m equal to u of t. And it's basically you plug in 1. You plug in 1 over here. And now you can take, again, you take Laplace of both sides, because this time we're solving for a solution x of t based on a specific initial conditions. Taking Laplace both sides. Now this time when you take a Laplace both sides, and particular for the first term or second term, the Laplace, the second order derivative, the first order derivative, this time you're going to have to take those initial conditions into consideration now, okay? Because you're not looking for the transfer function anymore. Okay, so m equal to 1 again. You should know this m equal to 1, b equal to 4, and this equal to 5. So we get s squared, capital X of s, okay, coming out of the first term, minus s times x of 0, x prime of 0. This is the Laplace transform of the first term. The second term, 4 times s capital X of s minus x of 0 plus 5 times capital X of s. And Laplace transform of 1, you look at the table, Laplace transform of 1 give you 1 over s, so 1 over s on the other side. All right, so that's the step after taking Laplace both sides. Now substitute initial values or initial condition values into the equation in here, and also group all the terms that's associated with x of s. We have x of s multiplied by s squared plus 4s plus 5. That's exactly the same denominator that you have used for finding the transfer function. And then minus 2. Because x of 0 is 0, only x prime is 2. Okay. And the equal to 1 over s. Okay, so now bring that 2 to the right side. So become 2 plus 1 over s, or in other words, it's s plus 2 over s. Okay, you bring the s to the other side. Sorry, 2s over 2s plus 1, 2s plus 1 over s. And then you solve for x of s. 2s plus 1 over s times s squared plus 4s plus 5. Here's your x of s. Remember what you're looking for, okay? So you're looking for the x of t, the output of the system. So x of t is just the inverse of this x of s. So again, right, here's where you had to somehow decompose this x of s into simple forms so that you can use the table. Decompose that depending on the type of the new denominator. So you look at denominator, there are two terms, s times the s squared plus 4s plus 5. S squared plus 4s plus 5, we have already shown that it contains complex conjugate roots. And s has a pole, s equal to 0. So this is fine. Then when you decompose this right into the simplest form, according to what we learned, for the s term, you just a over s, a constant over s. For the s squared plus 4s plus 5, you keep it as it is. And numerator should be bs plus c. Those are the rules, right? So you had to stick to the rule to simplify this into the simplest format. And the next step is to find constant value ABC. To find constant value ABC, I want you to do yourself to do it, is to compare coefficients. What's comparing coefficient? You have to write this fraction addition back into one single fraction first. And then compare the coefficients of left and right. The right side is 2s plus 1. And the left side, there's probably a little more complicated. So compare coefficient, set up equations. You'll have 3 equations to set up and then solve the 3 equations. And you get the constant value for A, B, C. Okay. So A should be 1 over 5. B should be negative 1 over 5. And C is 6 over 5. So try yourself, and you have solutions in the lecture notes. Okay. Once we get this step here, so now I plug it. So sorry, this is inverse of everything. Okay. Yeah. So I plug it into each one of the term at here. Okay. Inverse of A over S is very straightforward. It's just the A times U of T, right? So it's the inverse of this term. You have to manipulate a little bit, right? Yeah. So x of t equal to the inverse 1 over 5, 1 over s, and plus negative 1 over 5s plus 6 over 5 over s squared plus 4s plus 5. Yes. All right, so let's see. How do I manipulate the second one? Okay. All right, so I'm going to leave the numerator untouched, and the denominator, I will write it. I will write it as what's given the table, s plus 2 squared plus 1. Right, we did that for the impulse response. So A equal to 2, omega equal to 1. Okay. So now let's manipulate the numerator here so that we can use the table. First, Laplace transform, inverse Laplace transform the first term. That's straightforward. So just 1 over 5 times u of t. Okay. So let's go back to the table. This is how you should look at the table here. So you got the numerator already over here. You just have to manipulate you got a denominator here. You just manipulate the numerator to be the same format as this, either s plus a or either omega. Right, that's what the purpose of it here. Now you look at this one here. Right now, this is negative 1/5 times s. So if you want this numerator, you need what? You need this to be not just s. You need it to be s plus 2. Okay, so you need this s to be s plus 2. But if you change this s to s plus 2, basically, what did we add on? We added a 2/5, right? So we had to get rid of the 2/5 so that we're not changing anything at here. Is that clear? All right, so now we're inching further, right? So then you look at this term over the denominator, right? That's one fraction. That's 1/5 s plus 2 over s plus 2 squared plus 1. All right, so that exactly, so this is exactly what's in the table, right? So how about the next term here? This is 2/5 plus 6/5, which is 8/5, 1 over s plus 2 squared plus 1. So at this time, both of these two, okay, you cannot do any simplification, exactly a match to what's in the Laplace table. You can safely write down the inverse for both of these. First one, -1/5 times e to the power -2t, and then cosine t. Second one, 8/5 times e to the power -2t sine t. And then technically you should multiply u of t for either all of them, right? So the whole thing is a causal signal, just to make sure. And that's it, right? That's the response of the system when your input is a unit step signal. Right, so if you go over again, right, with the procedures, it's basically boils down to the same kind of question as to solve a second order differential equation using Laplace transform. And of course, you could even solve this maybe using a traditional time approach, right? But we're using Laplace approach, okay, to solve this second order differential equation. Any questions? Okay. All right, so all good. So for the rest of the lectures, so we have technically 1, 2, 3, 4 lectures left. We're gonna focus on the last topic. I mean, probably the last two topics. But one of the topics we're not tested in final. There are two topics we need to cover. One is called Fourier series, and another called Fourier transform. Fourier series will be part of the final exam, but not Fourier transform. Okay, so there are basically two things left. We're gonna show you what Fourier transform is, but this is gonna be tested. But this one will not be tested. So let's take a look at Fourier series first. Okay. Once you heard a series, I think, you know, for probably the first thing jumped in mind is Taylor series, right? So Taylor series is something you learn in the first year. If you have a arbitrary time function or x function, whatever function, right? So if you have a single function, a single variable, even multivariables, right? You can always rewrite this function with an addition of a series of a number of other functions. And this is the simplest format, right? Using summation sign. So basically, the original function, whatever the function expression is, right, could be represented using an addition, right? Infinite number of terms of number of other expressions. You add, when you add them up, then you get actually back this f of t. Now, if you choose only a limited number of terms, then it's not an equal sign, it becomes an approximate sign, right? So Taylor series, we use Taylor series a lot as an approximation of f of t, right? Especially if you only pick a limited number of terms instead of the infinite at here. So that's a Taylor series that you have learned in the first year. Okay? So it's a concept of approximation, how to represent this function using completely different ideas. It's like if just look at this function, you do not see at all, right? Behind this function, there are numerous other terms that when you add them up, you actually get back this f of t. So that's Taylor series. And Fourier series is a very similar concept. Okay? However, Fourier series operates on periodic function. So when you have a periodic function, so we'll show you these details later. Okay, when you have a periodic function, and it turned out that behind this periodic function, you can represent it using sine cosine terms. Right, so this one there's no sine cosine. This is just first order derivative, second order derivative of the original function. Okay, but as I'm going to show you, if you have a periodic function, behind the periodic function, it's all about sine and cosine. So that's what Fourier series is going to be all about. And you're going to see Fourier series is not that difficult, especially to calculate. Okay, yeah. So let me write down a few things. So the Fourier series and what it deals with are periodic functions. It's called f of t. And let me write down the final solution, and then we'll get down to the details. And it approximates this f of t. Okay. Yeah, see, again, a similar idea as Taylor series. Approximate this periodic function f of t as the following expression. Okay. All right, so this is the final result of Fourier series. So that's why we're going to get onto these details. But again, from a bigger picture, right, is that if you look at the expression, okay, all remember this is a periodic function on the left side. On the right side, right, there are a whole bunch of a constant, a naught, a n, b n. Those are constant. We're going to find it out. But the constants are multiplying a cosine term and a sine term. And then the cosine term and sine term at here, right, as n go from 1 to infinite. And omega naught is a frequency. Omega naught is directly related to the period of the function. So as you can clearly see, if you expand the right side, expand it out, you have infinite number of terms, and you have each term has cosine and a sine involved over there. So whatever your original periodic function is, once you express that using Fourier series, maybe your original periodic function is a box, is a sharp edge. You don't see the sharp edge anymore. All you see on the right side is a whole bunch of smooth cosine and sine and terms. That's what basically what Fourier series is all about. Okay. And we actually call the cosine n omega naught t and the sine n omega naught t. Okay. We call these two, we call them the basis for the periodic function f of t. So I'm going to cut to the chase and directly jump into how we can get this expression out of here. Okay. There are a few other integral tricks that might actually help you, but we'll see how much we use that, and then we can probably mention them in three examples. First, let's talk about the concept of periodic function. And as you can see, Fourier series focuses on periodic functions. So we have to understand, if you're given a function, is it a periodic function or is it not a periodic function? If it is a periodic function, then what is its period, right? So that's important first step information we have to be able to get. All right, so let's consider the following function. So for this function, I'm going to give you the graph right here. This is f of t is 0 to 1, 2 to 3, -1, -2. So here's a proper drawing of a periodic function or arbitrary function here. So if you have a function sketched like this, even if the question does not tell you what the period is, okay, so you need to be able to identify, okay, this is a periodic function, and what is the period for this function based on the graph. And that's the fundamental skill I need you to have. Okay, so you need to be able to identify the period. Okay, t naught. So how do I get to this, right? So that's basically fundamental definition of a periodic function means when you shift this function by the period of a t naught, then you should get back exactly the same function. So that's what mathematically how you define a periodic function. Now, because this is infinite on the left side here, infinite on the right side here. So if you shift to the plus t naught or minus t naught, the same thing, and you'll get back exactly the same function. So no change, right? That's how you can identify your t naught essentially. And more simply, you can look at the graph right here. Is that you can actually pick anywhere in the graph. So if I pick this from this location here, so then I will start to go along the time axis, okay, from here to here. And once I enter here, and then if you look at the next step, it basically start repeating itself now. Okay. Or if you pick it somewhere over here, then you go to the right, and then start repeat from here. Right. So, however, the length you have tracked from the beginning of your choice to wherever the points where it starts to repeat itself, and that is the period of this periodic function. Okay, yeah, and that's how you can identify. I said identify this t naught from this graph. So apparently for this periodic function, the t naught is 2. 2 seconds. So if it doesn't label anything, then just write it 2, right? 2 seconds, 2 hours, who knows? Yeah. It's just as simple as that. So that's the periodic function, okay, of this. Once you identify this periodic function, then next step is, so we actually can get down to the calculation of this for the Fourier transform. So the first type of Fourier transform, we're going to call this a trigonometric format of a Fourier transform. Fourier series. Trigonometric Fourier series. And the word it's sort of explains itself. Trigonometric basically, it's what this is what we're going to get. You look at this, it's all about trigonometry functions. Okay. So here's the definition or formal definition of a trigonometric Fourier series. For f of t with period of a t naught, then f of t equal, so basically I'm rewriting that equation. And this is the Fourier series for a periodic function with a period of t naught. And omega naught is basically equal to 2 pi over t naught. That's omega naught. And we call omega naught fundamental frequency. So sort of explains that because in the expression you can see the rest of the frequencies are all multiples of omega naught, right? So n times omega naught. So omega naught is called fundamental frequency. And there are a whole bunch of coefficients added here. So you have an and bn. So an, bn, and n starts from 1 to 2 up to infinite. And these two constants, we call them Fourier coefficients. Okay, so this is called the Fourier coefficients. And then you have another one, a naught, which is separated out. It's like basically at n equal to 0, right? So the a naught is called a DC component. A DC component. So I'll show you what this actually means, but I think you should know what DC means or AC means, right? DC basically is straight line, right? If you have a circuit, you apply DC voltage, you apply voltage at the constant value of 5 volts or 10 volts, right? That's DC component. AC means you have oscillating input to the system. That's called AC. As a matter of fact, you look at the rest of the part of the expression for Fourier series. So the rest of this is called the AC component. That's how you can maybe simplify the memorization of the Fourier series. There are two components. There's a DC components, there's AC components, right? I'm going to show you the formulas how to calculate A naught, AN, and a BN, right? Okay. And the other thing is, in the future, especially for mechanical, there's a course called vibration, right? So when you learn vibration, it's a lot about basically sinusoidal curves. Okay? And there's a term called harmonic motion or harmonics of a sinusoid. So when you look at this equation for the Fourier series at here, it's all about additions of multiples of fundamental frequency, omega naught. You have a 2 omega naught, omega naught, 2 omega naught, 3 omega naught, 4 omega naught, you're adding them all up, right? So these are basically called harmonics of the sinusoid. You have a sine 100 hertz, sine 200 hertz, and sine 300 hertz, 400 hertz. Right? So those things altogether, all of them called harmonics. Okay? Harmonics basically are integers multiple of each other. Right? That's basically what harmonic means. If you play music, when two harmonics together, it sounds beautiful. If not, then no, it sounds like noise. Okay? Yeah, not so beautiful. Yeah. Anyway, so the question next is, how do I get this A naught? How do I get AN? How do I get BN? As a matter of fact, this is a part of the Fourier series. Application of Fourier series is you can always decompose a sound, okay, any sound, into a multiple of Fourier series additions. So whatever we're talking, whatever you're listening, actually in the back, on the back of the sound, are these and these are there. So let's look at A naughts, AN and BN first. So I'm going to write down a few. Formulas. Okay. For some, you can take a look at the proof in the lecture notes, but I'm going to show you one simple ones, how A naughts can be derived here. Okay. So let's call this is equation number 1. Okay. So this is Fourier series of a certain periodic function. Let's call it equation number 1. Now let's integrate. So first, maybe let's see. Now this time I'm looking for the A naughts here. So integrate equation 1. Integrate both sides of equation 1. Integrate from 0 to the period of this function f of t. Integrate both sides. Okay, so if you integrate, then you get this expression. We want to only integrate for one period of the function f of t naught. Okay, 0 to t naught. Okay. Now, these two terms, okay, there's two terms. If you carry out the integrals of these two terms, okay, always remember omega naught is 2 pi over t naught. Okay, don't forget what omega naught is. Okay. If you calculate the integral of this, very simple integral. Okay, so cosine integral cosine end up with a sine, and sine integral end up with a cosine. Okay, and then you can substitute the limits 0 to t naught into the results, okay, of the two integrals, and you'll see they are both equal to 0. They're both equal to 0. And this is actually an integral tricks. So I listed a number of tricks in the lecture notes. If you're interested, you can take a look at it. Okay. So there's something to do with a so-called orthogonal function. Anyway, so you got a 0 for both of these terms here, so then you're left with just this term here, which is A naught times capital T, T naught. So apparently your A naught equal to 1 over T naught integral 0 to T naught f of t dt. So this is the result of how to obtain A naught. What it involves integration of f of t from 0 to t naught and then divided by t naught. That's it, right? So if I look at, for example, if this is a f of t we're looking at, then we're integrating from 0 to 2 for f of t. It's actually quite simple, right? When you integrate from 0 to 2 for f of t, and the remaining value between 0 to 1, so you're ending up with just the t naught times 1, right? And divided by t naught. And that's how you're going to get the a naught. So we'll show you specific 3 examples next. So very simple integrals you're going to see. So how about an and bn? Now these two, a little bit more steps of proof at here, but this is where I'm going to skip the proof from the lecture. You can take a look at lecture notes how the results are derived. Okay, so bottom line is an equal to 2 over t naught, 0 to t naught, f of t cosine n omega naught t dt, and n equal to 1 and 2 and up to infinite. That's the expression for an. Expression for bn, quite similar, except instead of a cosine, it becomes a sine. And that's bn. If you conduct the integrals for these 3 expressions in here, so then you get essentially all the information you need for the Fourier series. Okay. And let's take a look at example together and see how the values can be derived. Okay, so I'm going to use that periodic function to demonstrate. Any questions so far? Now, all of the formulas are given already in the formula sheet, so you don't have to memorize. But I still recommend, whenever you learn something new, just grab a piece of paper, right? Even if you don't know what you're writing, just write down for 10 times. Right? It's to get to know it. It's like to make a friends with this formula. Okay, so let's take a look at an example. I'm using this previous periodic function to illustrate. Okay. So we already identified the period is 2. Then omega naught is 2 pi over t naught, or 2 pi over 2 equal to pi. Okay. So before we actually calculate, let's do a very simple. Let's go back to this original definition. Now remember what a naught is, right? We said a naught is the DC component, okay, of f of t. And the rest of these terms are AC components of f of t. Okay. So of course, we can certainly calculate a naught by plugging the formula like that. But before we calculate, let me ask a question here. So here's your graph. This is the graph f of t. Would you be able to identify the DC component of this graph? What is the DC component of the graph? Anybody? What's a DC component? the line that was just drawn over here is the DC component. What do you think this value would be? 0.5 or 1/2. Right? That would be actually your A naught value. So let's verify if this is actually what we're going to get. T naught is 2, so 1/2, 0 to 2, and then f of t dt. When you integrate from 0 to 2, f of t exists only between 0 and 1. And the value of f of t between 0 and 1 is 1. So you literally just 0 to 1 and then integral 1 dt, which end up as 1/2. So that's exactly your observation based on the graph of this f of t. Okay. So I'm running out of time. So next lecture, let's look at the values of an and bn. All right. Yeah. And then we'll show a little more examples on Fourier series. So by the way, we have a last quiz 3, which is on a second order differential equation, non-homogeneous, using either undetermined coefficient methods or the variation parameters to solve that just one question, okay, the second order differential equation. Okay, so it's going to be either, I think, a Friday or Saturday, just as usual. All right, yeah. 1 sec, let me